When we're looking at rate laws, we might notice that we have this rate constant there, and it may not be super obvious as to what that is. And simply, it's just a mathematical proportion constant. And so if we take a look at our previous set of data, ta-da, from before, now that we had calculated our values for m and n, we can calculate k if we're so inclined. Remember, once we figured out our exponents, we have our official rate law. And that means we can actually plug in any of these values to determine that. We can take any experimental set, and we should come up with the same constant for each one. So we saw that we got the rate was equal to k times h2 times I2 for this reaction. And so it's simply a matter of plugging things in. One thing to note is that the units of these quantities here are always in molar. So we have molar, molar, and molar per second. Those are always the values that we use here. And so if we want to do this, let's take the data from experiment 6. Our rate is 43.3 times 10 to the negative 7 molar per second. We have our rate constant times the concentration of hydrogen, which I don't need to put in brackets, but we have 0.2 times 0.0808 molar. And so if we go ahead and solve for this, let's just do the number part first. Calculator. 43.3 times 10 to the negative 7 divided by 0.2 divided by 0.0808. And doing so, we get k equals to 2.679, or in this case only 3 sig figs, so 2.68 times 10 to the negative 4. And so if we want to consider the units, we're going to need to divide both sides by molar squared, right? To cancel out all of the molars on the right side. And in doing so, we get molar per second. And we're going to see that we can have very bizarre units for our rate constant. We can see that sometimes we'll have per molar squared per second, or molar cubed per second, or some weird other units. There's no, we can have even half, molar to the negative 1/2 power times second to the negative 1. So don't worry about the units necessarily. Don't worry if you see weird units. Still just do mathematically your way of finding out the units, right? Because we need to divide both sides of this reaction by, once I can figure out the numbers, 0.2 molar and 0.0808 molar. So these two molars cancel out. We're left with a 1 molar on the bottom and 1 second on the bottom. So that's where this molar negative 1 second negative 1 came from. We'll see for certain reactions, we may end up with, rate equals k times a to the 1/2 power times b squared or something. And in that case, our units are going to get really weird, right? We know we're going to have molar to the 1/2 and molar squared. The rate would be molar per second. And so we're going to end up overall with this with k equals whatever value times molar to the negative 1 and 1/2 power, or 1.5, we can say. We'll just make that easier. And then second should always generally be negative 1. So weird stuff can happen. So it's normal. You'll see weird stuff. So just be aware that these units can change. In terms of the actual number here, that number should be the same no matter what set of data points you use. We use the data from experiment 6. If you use any of the ones from 1 through 5, check it out. You'll see you should get the same value for k. It's a constant.